Alright. Okay, boleh mula. Okay, so this is what we left from not last week, last 2 weeks. So kita tengok Ziegler-Nichols. So this is the you have your mu, you have your dead band. So this is your dead band. So this is your rush time. So you get all what you need. You ada rush time, you ada dead band. So ada dua lah empirical model untuk untuk Ziegler-Nichols, method 1 dengan method 2. So method 2 is a more simpler calculation. This is based on the process reaction curve. So I've already uploaded Ziegler-Nichols punya original paper dekat dalam iFolio. If you cannot access from iFolio, please let me know. Saya boleh hantar dekat WhatsApp. I can put it here also, dekat WhatsApp class punya channel, Ziegler-Nichols punya original paper. Okay. So this is the date band. So this input should be close to a perfect step, but this was basis of equation. So if not, we cannot use the data for process reaction curve. This is empirical so sometimes you just have noise, so the output must be moved enough. So this is with a single step, you can see the signal to the noise ratio. So if we have this type of noise, can we use this in our calculation? Okay, so we assume that there is a step, then we have some delay. So this is date band, and then you measure what is your input, your rush time. Then you have bila dia dah rata ke atas tu, that will be your steady state. Then you take the 67%, that will be your rush time. So you can use a Ziegler-Nichols approach for 2-point methods. Then you find the PID controller parameter for the recommended by Ziegler-Nichols first method. And then this is the examples. You use this thing, and then you apply dalam your MATLAB, then you can see macam mana the response. Okay. Ziegler-Nichols second method, this is ultimate cycle. So dia punya tuning dia slightly simpler. So use open loop. Second method, use closed loop. So if the process open loop is unstable, or if the stable but does not give the S shape as you want in the open loop, so dia tak ada dead band. So you cannot find the dead band, and then you cannot find what is the slope. So second method is slightly easier. So you put the process under closed loop control, and then you use a proportional controller. You varies the gain, and then you create a small disturbance in the loop by changing the set point. Means that you change the input, and then you change the gain. So it adjusts the parameter, proportional gain. So you varies the input. Let's say input daripada 1 jadikan 2 atau menjadikan 5, and then you bagi gain dia lagi besar. And then you record the gain, and sampai dia start to oscillate. Once they oscillate, you find the frequency of the oscillation, and then from here you can calculate what is the apa nama tu, daripada frequency of oscillation dengan the gain, then you can find what will be your P PI dengan PD, PID. Okay. So sometimes dia ada apa dipanggil sustained oscillation. So you change the set point, you change the gain. Say in this example, set point you change daripada 1 jadikan 200 degree Celsius, and then you change the parameter, you increase from 1 to 3, then daripada 3 some oscillation. Let me see whose mic is on. So I'm asking to, sorry. Somebody accidentally switch on the mic. Okay. Then you have your, when the oscillation frequency is stabilized, you have a constant amplitude of oscillation. So this is when the actual frequency being used. So you just change your set point dengan gain. So you set the gain sampai they oscillate, and then you slightly adjust the input so that you have a constant amplitude of oscillation. Then daripada situ you dapat what is your period and what is your gain. Okay. So you can apply, masukkan kat dalam situ. So this gain is actually sama dengan what you gonna get dalam your root punya criterion. Okay. So you just apply your untuk apa nama tu, based on the absolute gain for PID, KC is 0.6 gain of the calculation, and then you have for PID you have 0.6 times the oscillation. TI is 0.5 times the period of oscillation. TD is 0.125 of the period of the oscillation. You can see kat sini TD is about berapa kali ni? 4 kali lagi kecil daripada TI. So this is quite normal. In some, kalau you nak main teka, selalunya TD kita set dulu. Nanti kalau if you look at the assignment yang saya bagi, saya suruh you pakai visual punya methods. Nanti kita tengok visual methods. So selalunya in visual methods, kalau kita nak try, we set TD to be 10 times smaller than TI. That's a rule of thumb. Okay. That's another methods of finding the ultimate gain KC by using root locus. We just move around the lock key sampai dia cross S equal to 0, then you get your gain. So kalau macam ini, this is not experimental. This is based on the simulation using MATLAB. So you ada dua lah, satu pakai the real experiment in a closed loop system. Satu lagi you buat closed loop, you simulate pakai MATLAB and you look for your ultimate gain for the oscillation. Kalau macam pakai MATLAB simulation, sorry, not just MATLAB. If you simulation, then you are not apa nama ni, you are not adjusting the set point to get the oscillation. You just drive the poles so that you know that that location will oscillate. Okay. So kalau you tengok ke sini ni, dia tak ada S shape. Dia ada mula-mula tu kalau tengok sini dia ada uh, slightly apa dead band. Lepas tu dia become linear slope. So this is the closed loop set point response. From the previous examples yang saya tunjuk tadi, and this is closed loop stable step response. So ini MATLAB code, ini code yang lama tapi still boleh pakai lagi. Kalau yang baru punya, it will be a lot more simpler than this. Okay. So this is apa nama ni, simple conclusion of second method. You set Ti to infinite, Td to be 0, and then use a proportional control. You just change dia punya set point, means that you set change the input slightly, and then you increase the gain Kp from 0 to a critical value where the output state start to oscillate and produce a constant oscillation. That will be your critical gain. Okay. So once you get your critical gain, then you'll get your period of oscillation. Daripada situ you find what will be your oscillation period. That will be so you will get those two values, critical gain and period of oscillation. Then the tables is good enough untuk bagi what will be the Kp, Kt, Kp, Ki, and Kd. This is another example. You boleh tengok macam mana nak buat tuning. Okay, boleh tak? Kalau misalnya kata macam dia S shape macam ni, and then you use second method, boleh. So second methods ni based on closed loop punya oscillation. First methods, if you have just the open loop, it's not used in the closed loop. So that's another examples. You can take a look at the examples. So you get your critical gain. So nak dapat critical gain, you boleh pakai root locus, you boleh guna root criterion. And then you just drag this thing. So this is another example. Pakai root criterion to get your Kp, your critical gain. Sama je. So once you get your Kp, and then you masukkan your Kp dalam sini ni, then you will get your what will be your J omega. So this thing you can use MATLAB also to do this thing. Kalau pakai root criterion. Dalam MATLAB ada tak root kalau yang lama ada, yang baru saya tak sure. Kita boleh tengok. Okay, kalau pakai calculation ni, masukkanlah your gain Kp, masukkan dalam situ. But you have your ini kan, your apa nama ni, kalau tengok sini ni, this is your transfer function. If you have your Kp, then you get your closed loop. So Kp over S plus 1, S plus 5 plus Kp. So you from root criterion, you masukkan Kp dalam this equation. Then you look for what will be your oscillation frequency. So once you get your frequency of oscillation, then you gonna get your period. Macam sini lah. Your period is 2 pi over omega. Okay. Sama je. Okay. So kalau masukkan, boleh guna MATLAB to do the simulation. Kalau bagi input step macam mana. So this is Siapa yang nak masuk ni? Vishnu terkeluar masuk balik. Vishnu jangan lupa pukul 3 nanti ICAPS punya award ceremony. Jangan lupa. Kalau menang Gap, siapa dalam ICAPS ni? Gap, Vishnu, siapa pergi seorang? Siapa pergi geng-geng masuk ICAPS. Kalau menang boleh belanja saya makan sate. Saya nak makan sate dekat mana sedap. Kalau tak ada sate, pergilah makan mana-mana yang sedap lah. Belanja saya makan. Okay, so this is the electronic PID controller. So this is your P, this is your D, this is your I. Okay. Apa masalah dia dengan PID controller? Kalau kita tengok dekat PID controller electronically, saya ada assignment nanti. Saya nak share soalan dia. Kalau pakai circuit maker, saya dah buat dulu-dulu. So this is your PID controller. Kalau tengok dekat sini ni, dekat integral. So this is your CI, this is your R. If you take a look at this will give you a certain slope. Dia tak bermula dengan S equal to 0. So dia punya poles ya is 1/RC. So kalau you bagi C ni terlampau kecil, R terlampau besar, then this thing will be very very slow. So you bagi dia tak ada capacitor is not charging. So dia very slow. So this R ni ada value dia. Dia ada maximum value of R. Kalau you bagi R ni terlampau besar, sebab you nak dia RC kan. So this kalau you nak R ni terlampau besar, then you will have a problem. Sebab nanti your output will be very very small. Bila you bagi gain from your PI, from your I, bila you bagi gain dekat sini, R5 you bagi gain, masalah dia you are not amplifying the signal, you are also amplifying the noise. Itu masalah dalam implementation of this type of controller. Kalau kita buat electronic. Sama juga macam ni. So this is for derivatives. You want to make your C dekat sini ni. So this and this, dia ada gain, then this thing will adjust the gain. Again, this and this ratio will be very critical. Kalau bagi value kat sini besar sangat, dia jadi lain. Bagi kecil sangat, dia jadi lain. So there will be some sweet value for this lah. For the ratio, kalau integral punya ni, dia ada ratio of R dengan C. So R tu ada limit dia, upper limit and lower limit. C pun ada upper limit and lower limit. So selalunya C ni kita tak bagi sampai 0.1 picofarad, tak adalah. Kita bagi dia in the range of nano, macam tu 10 pico still boleh lagi. Tapi bila nak bagi macam tu, then your C must be very good lah. Tak boleh pakai capacitor mica, tak boleh. Kena pakai something like silver mica. Kalau bukan silver mica pun very nice polystyrene. Polystyrene. So kalau this is a parallel form and this is a series form. Dua-dua ni ada pro and con. Kalau tengok sini ni, this is your D and this is your I and this is your overall P. So this is your PID controller. Dia ada pro and con for this. So this is your, ini dah. Kalau tengok this is the ni dia punya KP apa KP KI dengan KD. Okay. Okey, kalau you tengok sini ni, this is examples yang saya ambil pada buku. Kalau you tengok sini ni, this is for visual tuning. So kita nak ada oscillation, tapi kita tak nak oscillation yang terlalu banyak. So this is under, when x equal to 2, this is under, x is a ratio. Dia panggil reaction, dia panggil apa, apa nama ni, ratio untuk PD, sorry, untuk I dengan D. So kalau you bagi dia punya ratio dia under, when the ratio is big, this is when the ratio is too small. Ratio ni tak semestinya 0.5 yang bagus. You have to change the ratio, play around depending on the requirement of the controller. Okay, we can see from the reaction curve tuning methods is very sensitive to the ratio of the delay and the time constant. So due to this, so ada satu orang lagi lah, dia kata ratio tu tak boleh macam tadi tu. 0.4 ratio of PD dengan PI dengan PD ni tak boleh 4. There must be some other value. So di Cohen-Kuhn came up with a different ratio untuk KP, KI dengan KD. So Cohen-Kuhn carried out further studies and find the control setting, which is based on the same model, tapi dia lead to a weaker dependence on the ratio of delay and the time constant. Ini sama je, beza dia punya parameter je, dia punya apa, dia punya ratio-nya je lain. So this method works well on the process where the date band time is less than 2 times of the time constant. So kalau misal kata kita tengok sini ni, so this is date band, the tau dengan the time apa nama ni, date band dengan the time constant V naught, dengan nu naught. So this method works well when the date time is less than 2 times the time constant, suitable for use of the self-regulating process based on characterization of the process by a simple first order with steady state gain K and time constant and the date time. So in order to do this, a step response of open loop has been obtained, and then the response also known as the process reaction curve, and then from the reaction curve must cover the entire test period from the introduction of the step until the system reach a new steady state. So selalunya kita bagi dia 2 step. First step kita dapat 1, and then kita buat another step response. Kita increase, let's say dia sekarang ni 1, and then kita bagi step. So the first one is the value of the set point is 1, and then after a certain period of time kita increase the step, kita increase the set point daripada 1 jadi 2. So this will take a few minutes. Ini kalau ikut actual system, takes a few minutes to several hours depending on the speed of the process. So as you know, Cohen-Kuhn, Ziegler-Nichols, this is for chemical reaction. So kalau dalam electrical, kita tak nak lah sistem ni punya steady state tu, few minutes or several hours. So kita nak guna untuk track kapal terbang, tak boleh lah 1 jam lepas tu baru kita nak track. Okay. Cohen-Kuhn sama je. Cohen will be based on the first order plus date time. So kalau you tengok sama, it will give you the S shape lah. For the step change in the control output with the magnitude of delta M, then we'll have this, where the CS is the output of the process. So ini, so kita bagi first step, second step. Selalu kita ambil first step, second step. Kadang-kadang you can just use a single step. Tapi selalunya Cohen kun ni kita buat 2 step. Ini dah reach steady state, kita increase the set point. So from 1 jump to 2 and then kita wait for the reaction curve. Okay. So this is the gain. And then this is the rush time. Okay. From this, just plug into the Cohen tuning methods. Okay. So kalau Cohen kun, kita tengok untuk the ratio of 0.1 dengan 0.5. Then you can see when the ratio apa nama ni of this date time dengan apa date time dengan rush time. Is 0.5. Then you have 1 dengan 0.1, dia tak bagi kesan sangat. Kalau tadi kita tengok 0.1 ada kat atas, 1 ada kat bawah. Kalau 2 lagi kat bawah, so dia tak banyak bagi kesan. So it'll be bagus untuk self regulation. Dia tak ada senang apa dia punya, selalu kita panggil benda ni very stiff. Dia susah untuk, once you control, it will be very stiff. So you nak change the system tu, kalau ada disturbance ke apa ke, dia tak akan mudah untuk bergerak. So kalau control engineer selalu cakap benda ni very stiff. Okay. So as I told you earlier, lag lead controller, lag lead compensator ni very much like a PID controller. Cuma kita let satu apa nama ni, one extra poles to be infinitely far compared to the rest. Dia settle cepat. Okay. So kenapa saya tunjuk ini? Kejap lagi kalau tak hari ni, minggu depan kita akan tengok loop shaping. Kenapa saya nak cerita loop shaping? Sebab kalau boleh saya cerita sikit on QFT. So QFT ni basically hampir sama je dengan loop shaping. Tak jauh beza. So this is the lag lead controller. So this is the magnitude, this is the phase. So the effect is about the same as the reaction in PID. Okay. So Ziegler-Nichols closed loop tuning methods. Satu lagi dia panggil lambda tuning. Ini saya tunjuk aja lambda tuning. Tapi lambda tuning ni tak masuk dalam exam. Tapi ini antara benda yang banyak dipakai lah, lambda tuning. So, ada banyak dalam untuk PID controller macam mana nak tune. Ada yang auto tune ada yang pakai backwards apa dia panggil ni? Uh, backward uh, backward calculation kan. Alamak Allah. Saya lupa lah nama ni. Dia pakai backwards punya computation. Means that you get the response and you have the system. So kita variskan dia punya gain dia, kita pakai backward. Kita tengok banyak mana dia lari. So ini biasanya dalam apa dia panggil ni? Saya punya student buat benda ni, Fakari buat ni. Dia buat macam tu lah. So you have your response macam mana kita nak. So we have the system, and then kita variskan P, variskan I, variskan D. So daripada situ kita try to do some adjustment. Dia kira. Ada pakai backward punya calculation, and then you will get what is your P value yang sesuai untuk dapatkan the response KI dengan KD. Ini ni ada satu student saya buat lah untuk satellite. Okay. So this is lambda tuning. So the lambda tuning is also based on the ratio of your date band dengan your rush time. So dia ambil rush time dia daripada 0.283 dengan 0.632. So this is the T1 dengan T2. So this is dipanggil process time constant. And then you have your TD. So this is dia ambil from the from the TP. So TD is T2 minus TP, the tau. So this is your tau. So T2 minus the tau. So this will be your date time. So this is basically what you want to calculate. They're doing it date time. The gain is delta Y over delta U. So this is the gain. So sama je. So instead of dia pakai date time dengan rush time, so kita kira lain lah dia punya proses dia ada process time constant dengan process date time. Okay. Lepas tu dia ada satu design closed loop time constant. So dia variskan value typically 2 to 3 times the process constant. So this lambda is the one that you want to tune. Okay. So this is how you want to implement lambda tuning. You filter time constant. The filter time constant should be less than 1/5 of the process time constant. The closed loop time constant is usually greater than the process time constant. Okay. Dalam your assignment, saya dah bagi motor tu punya closed loop. So the motor punya closed loop is taken from UTEMS ke UTHM punya paper. So you pakai benda tu. So you pakailah Ziegler-Nichols, Cohen-Kuhn untuk tune the PID. You boleh pakai closed loop boleh, you boleh pakai Ziegler-Nichols first method, second methods boleh. Kalau you nak first method, you buat first method, second method, you nak buat second method boleh. You nak buat first, second method pun boleh. Lepas pada tu yang penting sekali is visual tuning. So you dah tengok Cohen-Kuhn, you dah tengok apa nama ni? Saya dah you dah tengok apa? Ziegler-Nichols first method, second method. Selalu orang guna second method sebab dia closed loop. Sometimes orang yang malas dia akan gunakan first method. Sebab first method is easy, you have the step response. Okay. Now this is the one that being used quite a lot. Dia panggil visual tuning. Visual tuning ini dia tak gunakan apa-apa methods. This is based on the response. You bagi step, dia jadi apa dekat output. Daripada situ, you tune, you change P, I dengan D value so that you get the response as you wish. So apa yang kita nak tengok? Kita nak tengok dia punya response dia oscillate banyak ataupun very slow. Kalau very slow ni dipanggil sluggish response. So how to improve the performance of the loop with no algebra? Based on the response saja. Tak payah nak calculate apa-apa. So this is the one that being used quite a lot. Dia panggil visual tuning method, visual loop tuning methods. Sorry, saya allergy kuat. Mata saya sepet jadinya. Tak boleh buka mata. Okay. So first you look for instability. Dia ada oscillation ke tak? If there is an oscillation because of excess feedback or being perturbed by previously by another process. So the procedure is to put the loop in manual, and then you in the manual loop the process appear to be to settle down. So kita tengok dia apa dia punya response dia. And then kita tengok if the oscillation caused by too much or too little gain in the forward gain Ki ataupun Kd or in the combination. So macam mana kita nak tahu? Kita just vary some of this gain. Okay. If the value of Im is less than half of the oscillation period, tau, so first you increase the value of integral. And if the value of integral is longer than the oscillation period, so it is safe to decrease the gain, your proportional gain. So you tengok, sistem tu ada apa? Dia oscillate, tak oscillate? Slow sangat ke? Kalau slow sangat, it's okay to lower the gain. So kalau misal kata macam dia ada deadband yang panjang sangat, then increase the value of your Ki. Kalau dia unstable, kita tengok dia oscillation, dia punya oscillation period dia macam mana. And then one of the parameter should be reduced. So in this case, you reduce your I. Kalau macam ini, it is okay to increase I. This is you need to reduce I. For non-self-regulating process, you use the longest value of I as much as possible, or completely remove the integral action. So you set this thing to be infinite, so dia tak ada kesan. If the problem persists, then you lower your gain P. So this is the one that yang kita selalu pakai. Sebab kadang-kadang to get mathematical model susah. So kita tune based on this visual. Kita tengok dia response. So kalau dia punya response dia kalau the system tu terlalu slow, sluggish, then usually there is no derivative action. So the value of IM is too long, terlampau besar. And then the value of gain is too small. So it's safe to increase the gain, reduce the I, and increase PD. So this is typical. So kalau the system tu sluggish, slow, so you set the I to the longest, and then set your derivative to be 0, and then place a controller in manual mode. Then you increase your gain. Okay, so you repeat this thing sampai dapat one cycle of process output swing. So this is swinging in one cycle. Dia swing. 1, 2, lepas tu dia mati. Kalau ini 1, 2, 3, 4 ini setengah cycle. This is one cycle. And then the steady state. So once you get this, you place a controller in manual immediately put the controller back into auto mode. Means that you introduce the feedback, and then you masukkan balik dalam, so that you can adjust PI dengan D, and then we get a new PV RAM back to a set point about half of the fastest as it move away from the set point. So the response with a reasonable gain, dia ada one complete cycle, and then you increase slightly KI, and then kita dampen this thing dengan your KD. This is a tuning map for gain P and reset all the PI. So this, kalau sistem dia macam ni, tengok. Kalau macam ini, this is too, dia punya gain is too small. This is gain too high. They start to oscillate. This thing tak ada oscillation. Kalau macam ini, reduce KI. So this is increasing the reset. So if you do this thing, you will reduce your KI. You increase gain, you reduce KI. So kalau you tengok sini, dengan sini, you can see ini dia punya oscillation dia dampen, ini dia become unstable if you increase your KI.
Pinjam tak cinta. Saya lagi sangat sama.
Kereta kat situ, Aisyah ambil lah kuncinya. Sorry, ada commercial break kejap. Ada orang tu tak ada duit nak guna touch and go bapak dia. Okay. So kalau you tengok sini ni, you can see apa? Ada orang nak masuk ke apa ke? Okay, tak ada. Kalau you tengok sini ni, you if you take a look here, then you can see if you increase, it will settle like this. So if you add derivatives with the best timing achieved with the proportional and integral, then you letak D, dia jadi macam ni. Period increase, dia punya peak time dia pun increase. MP dia, magnitude of peak also increase. Kalau kalau you kalau you add jadi macam ini, added to the increase integral. So kalau macam ini, you increase integral so that dia jadi macam ni. Kalau too much derivatives, it will be like this. So first, kita bagi dia PI. So bagi PI, and then introduce T. Okay. Auto tuning, saya tak masukkan lah dalam apa, tak ada sebenarnya dalam syllabus. Tapi memang selalu ada auto tuning ni, pergi mana-mana pun orang akan cerita pasal auto tuning. Auto tuning ni let the PID tune by itself. It will self-adjusting the P, the I dengan D. So you don't need to do anything, it will adjust by itself. So how can we do this thing? So the process is nonlinear or operated under widely varying condition. So you need various combination of tuning parameter for different operation condition. So this thing you can accomplish by using previous experience yang operator dah buat. Kalau dia buat macam ini, dia letak P value je macam ni, KI, KD value, it will looks like this. So based on this parameter, kita masukkan di dalam jadual. So the process of characteristic will change rapidly. So you have your frequent manual changing and tuning parameter cannot be expected to be able to produce satisfactory result. So the user doesn't have the knowledge of experience for the successful manual tuning. So kadang-kadang ada orang guna black box tuning, black box PID. So you don't need to know the system. So dia pakailah artificial neural network to do the tuning. So dia masuk, dia pakai previous value, previous experience, let the machine learn by itself. So ini AI lah, artificial intelligence. Kadang-kadang kita tak pakai macam tu, kita pakai auto tuning tapi yang lebih robust. Saya pun tak ingat apa benda yang saya buat sebelum ni. Kalau saya ingat, saya beritahu. Satu lagi dia gunakan table. Dia panggil schedule tuning. Satu lagi dia pakai on demand tuning. Satu lagi dia pakai online tuning. Online ni it will change. Dia tak ada break off. Dia continuously dia will change. Kalau jadi macam tu, dia terus tukar. Siapa yang tak jumpa pula siapa menyanyi ni. Siapa menyanyi ni? Sampai ke bawah. Vishnu tak ada mikrofon. Vishnu bisu. I don't know whom should I mute because I cannot see. Okay, tak apalah. Okay, satu schedule tuning. Dia contoh dia kalau macam sistem tu pagi lain, tengah hari lain, petang lain. So kita based on time. Pagi this is the parameter, tengah hari this is the parameter, malam this is the parameter. Contohlah. So this is schedule tuning. Ini pakai, dia panggil gain scheduling. So dia ada gain based on the schedule. Kalau satu boundary 0 to 30%, so this will be your P. I dengan D. Kalau region 2, this will be your this. Kalau region 3, this is. Macam mana dia nak decide region 1, 2 and 3? Kadang-kadang dia pakai fuzzy logic to define what is the region. Kalau macam ni dia tak pakai fuzzy logic, kita pakai boundaries. Macam mana nak tahu boundaries? Senang. Kita boleh pakai auto correlation. Kita correlate between the response yang you nak dengan response yang keluar. Kita tengok banyak mana dia correlate. So kalau dia correlate banyak macam ini, this is region 1. Kalau dia correlate tengah-tengah, nak correlate sangat tak correlate langsung tak, region 2. Kalau langsung tak correlate, region 3. So ini based on auto correlation pun boleh juga. Gain scheduling ni paling banyak pakai lah. Paling banyak pakai gain scheduling. Kalau kapal terbang pakai gain scheduling. So on demand tuning, kalau dia open loop terus pakai Ziegler-Nichols lambda tuning. Kalau closed loop dia pakai relay feedback auto tune motivated by Ziegler-Nichols closed loop and then dia tune. Ataupun the user pakai tune button to start the tuning procedure which carry out automatically. Ini untuk operator lah, dia ada satu PID controller box. Kalau dalam apa nama tu, kalau your third year lab tu apa dia panggil tu? PLC. Dalam PLC punya block tu dia ada PID punya controller block. So dia pakai benda ni. Ini untuk PLC. Untuk apa, on demand tuning. So kalau ini PID is on, this is for the tuning. So kita switch kejap untuk dapatkan certain untuk dapatkan parameter, and then kita tune the PID, kita switch back the system untuk PID with the controller. Okay. Alright, so we'll take a short break. Nanti kalau ada soalan, you boleh tanya. Saya bagi break 3 minit untuk awak ambil air. Saya pun nak minum air sikit. 3 minutes break. Untuk tanya apa-apa. Oh, saya tak boleh nampak. Oh, ini siapa yang gelak ni? Muhammad Fauzi. Oh, gelak. Ni dia main game ni kot ni. Mobile Legend ni jadi tergelak. Tak apalah. Okay, so I will stop so I'm done with the PID. So 10-5 minit saya start balik. Conclude cerita pasal your assignment and then kita akan start dengan benda baru which is loop shaping. So esok kita buatlah the PID punya assignment. So hari ni saya cerita loop shaping and then you will use the same thing and then you pakai loop shaping untuk tune your controller. So no more PID lepas ni. Lepas ni is loop shaping. So you can also introduce some value in your feedback. How much gain that you can give. Okay, kalau saya ambil saya punya whiteboard. Kita conteng sikit. Untuk introduce some QFT. Okay. I found a very good note by Alberto Bompora from the University of Trento, Italy, on look shaping. So this is a very nice note. I'm very interested to use this note for the class. So I'll do a few things. Okay. Let's say kita ada. So this is your G of S. And this is your controller. So this is your system. If I have this H of S, either saya nak masukkan ke sini, or H1, or saya nak masukkan ke sini. So by introducing this H1 dengan H2 in the system, this also will act as a compensator to the system. So what are we doing over here? These two things. Kita ambil output, kita filter output. I hope you can see this thing. Kalau tak nampak, bagi tahu kat chat. Kita ambil output. So instead of we just bagi output biasa, instead of bagi unity feedback, kita change, kita filter the output. And then we tune the output. Banyak mana kita nak fit dia masukkan kat dalam. Then this thing will also change the overall characteristic of our system. Okay. Contoh. Let's say you ada kapal terbang. Kita tengok banyak mana dia bias apa. Say you ada kapal terbang. Bila angin tolak kat tepi, kita tengok banyak mana dia punya yaw dia berubah. So daripada yaw berubah, kita lawan dia balik. Banyak mana dia kena berubah balik. So kalau dia corner 1 degree, kita bagi dia reverse 1 degree. So by introducing this, we will stabilize the system. Itu contoh. So selalunya kalau dalam kalau dalam kapal terbang ataupun dalam helikopter, kita gunakan rate gyro for this. We use a rate gyro and then kita implement terus. Kalau tak, apa kita kena buat? Kita kena ambil rate integral gyro, rate, kita integrate dia, then we are feeding the we will feed the angle. And then our input is angle. See, our input is angle. And then kita bagi rate integral gyro. So this is, ini rate gyro contoh. Ini selalu kat sini rate gyro. So this is rate integral gyro. So this thing bagi rate radian per second. So this is just radian. So ini angle. So kalau kita bagi macam ni, kita boleh terus bagi feedback. So ini selalunya kita panggil inner loop controller. So banyak mana kita nak bagi benda ni? Banyak mana kita nak masukkan rate ni, kita nak bagi gain kat sini. From this rate. So if we look at this, any poles kat sini become zeros. any zeros kat sini become poles. So kalau rate kat sini is zeros, so bila kita bagi dia feedback, it act like a pulse in the forward loop. So ini yang selalunya kita gunakan dalam kapal terbang, helikopter, dengan benda-benda yang kita nak dia ada instant effect. Jadi dia boleh bergerak laju. So ini dipanggil inner loop controller. This is outer loop controller. So this is the forward loop controller. So when you have ini, kalau kita buang benda ni, when we have this, ini selalunya dipanggil PFT. Kalau kadang-kadang yang boleh tengok. Quantitative Feedback Theory. So this controller will be easy lah. Let's say this is a PD controller untuk motor, senang. And this is the straight gyro. So overall it act like a PID controller, tapi dengan kesan yang lebih cepat. So you will get overall, you will get the output punya response to be more responsive. Dia tak ada sluggish saja, more responsive compared to just PID controller. So apa yang kita nak tengok hari ni is PID. Saya dah share. Tak apalah. Kalau tengok dekat nanti, saya tak alam, tak apa. Nanti kalau tengok, tak ada orang chat, kosong chat lah. Semua tak inform saya. Okey, tak apa. Kalau kita tengok kat sini, apa nama ni, hari ni kita nak tengok is loop shaping. Macam mana kita nak tune controller. It can be PID controller. Kita nak tune from the frequency response punya perspective. Ziegler-Nichols, Cohen-Kuhn, ini semua time domain. Kalau kita nak tune dalam frequency domain macam mana? Selalu you tune sama ada yang paling senang sekali sebelum ni yang awak belajar, you tune everything dalam S domain. Kita tengok pulse dia gerak mana, zero dia macam mana, kat mana, pulse dia bergerak macam mana. Kalau dalam root locus kat situ, okey kita nak macam ni, analogous to time domain macam tu. Tapi kalau benda ni kita nak tengok dia dalam frequency domain, apa sebenarnya a relation between frequency domain pada time domain? Kalau still remember when you learn your circuit theory in your second year, there is a relation between frequency domain dengan time domain. So this is the linkage yang kita nak establish dalam loop shaping method hari ini. Okay. Let me stop share so that I can show you the screen, my whiteboard. Saya akan tunjuk sikit. So this is apa relation kalau kita tengok QFT. So macam mana kita nak dapat relation between time domain dengan frequency domain? Apa relation between time domain dengan frequency domain? How can we relate this? Anybody? Saya onkan chat. Tengok. Where is my chat? what is the relation between frequency domain dengan time domain? There must be some relation between frequency domain dengan time domain. So tak apalah. Susah sikit ni kalau so, dalam frequency domain kita ada dua benda yang kita nak tengok. Satu gain, satu lagi phase. So from these two, kita boleh reflect dia dalam time domain. Ini awak dah tengok banyak dalam your electronic. Kalau dia react macam ini, what will be in the time domain? Kalau the gain phase macam ini, what will be in the time domain? Contoh dia lah. Let's say this is a low pass filter. So this is your phase. Ini daripada kosong. Kalau ini kosong, kosong sampai sini ni, this is 0.1. So this is 1, 0.1. So dia dah start. This is 45 minus 90. So kalau macam ini, time domain, you can see this is apa, dia akan ada this is the cut-off frequency. Cut-off frequency, this is your tau. Cut-off tau. So you can see the relation. If you have some phase, changing of phase, then you can see how much this thing will change into this. So you have to establish this relation between frequency domain and time domain. I'll come back to this later. So saya akan okay. Alright. So kalau kita tengok kat sini, so I'll go back to apa nama ni, kertas conteng dulu. Saya nak bagi contoh op-amp dulu. So if you cannot find the relation, kalau tak dapat nak establish the relationship between time domain dengan frequency domain, susah sikit kalau kita nak belajar control. Sebab kita tak tahu apa when the system to change, what will be the effect sebenarnya dalam time domain. Kalau the system tu sendiri yang berubah. Dia ada, kalau KFT dia ada bounded input, bounded output. Let's say I have a op-amp. Let me unshare the screen. Stop, share. Okay. Let's say I have the op-amp. Okay. Op-amp ni dia ada open loop gain. So this thing sama juga dengan kalau kita tengok kat dalam control system, this is something like this. This is gain. Unity feedback. Gain kat sini ni contoh open loop gain 300,000. So this is 300,000. Apa yang kita dapat kat sini? Kalau macam ini, saya masukkan satu volt, saya keluar dapat satu volt juga. Maksud dia kat sini ni, kalau saya masuk satu, saya dapat satu juga. Satu tolak satu, saya dapat kosong. Kosong kali 300,000, saya dapat satu. Betul? Kosong kali 300,000. Kosong kali 300,000, saya dapat satu. So this is impossible. Apa sebenarnya kat sini? So this is your error sebenarnya. So this is your error. So apa yang kita nak? This error to be very small. The smaller the error, the better. So kalau macam ini, kita nak bagi error ni lagi small, kita kena bagi gain ni lagi besar. So maksudnya ini error ni 1/300,000. Kalau saya ada sini 800,000, maksud error ni 1/800,000. So I will make this error to be very small. Kalau misal kata output saya macam ini, my gain ada some response like macam tu. Say this is my gain amplitude, contoh lah. And then my output will have something macam tu ke. So kalau saya fit this thing back, saya tolakkan dengan satu, so dia akan ada reverse, and then I have the error. So this is the things yang kita nak tengok macam mana sebenarnya this error, how the error will actually behave. Itu yang sebenarnya kita nak tengok. Because this is the output, ini output, this is output. This output kita tolakkan dengan kita punya input, that will become your error. So error times the system will get the output. So kita nak tengok macam mana kita nak buat satu controller so that this controller actually will modify the error signal. So kalau kita ada certain frequency band of the system, and then output tu ada certain frequency band, so kita nak filter so that the response, let's say this is tak nak macam ni lah, susah, sini susah. Let's say saya punya sistem saya something like this. Ini dekat 100, ini dekat 4,000. So saya sistem saya something like this. Contoh. Apa yang saya dapat kat sini ni, ni contoh lah. Ini. Salah lah contoh sini. Okay. Let's say saya ada something like this. Ini 100, ini 400. And then saya punya output ni ada some kind of this. So I have to change my error signal so that my error signal will only in this range. Dia start daripada 100 baru dia on. Saya tak nak sebelum 100, my error signal tu dah ada. Kalau saya punya error signal ni dah ada before 100 Hz, meaning that my response will not be as what I want. Sebab saya punya apa sistem saya will only start at 100 Hz. Tapi kalau saya nak, if I want the system to be slower or faster, and then the response is like this. Let's say ini daripada 1 Hz. Dia macam tu, output dia. And then I want the system punya output dia to start with a 10 Hz. Then saya akan amplify this thing from 10 Hz. So that 10 Hz will appear at the output. Kalau kat sini dia increase, let's say saya nak ada apa, saya nak extend the frequency to be at sampai 10,000. So saya kena increase lah from 10,000 tu. Saya kena bagi gain. So that is basically what we are trying to do today. Dia panggil loop shaping. Okay. So that will be what we are going to do. Share screen, loop shaping.
Cik,
Yeah.
maksudnya error dia kena kecil tapi tak boleh kosong.
Error tu kita nak as small as possible. Sebab error tu lah yang bagi error, your steady state error, everything error, start from error. Kalau boleh, you tengok kan, you nak ada apa benda error tu to be zero. Kalau error kosong, means that you have no error.
Tapi kosong darab 300,000.
Kosong darab 300,000 takkan dapat satu. So error tu sebenarnya ada. Error tu is 1/300,000 lah. Kalau misal kata your gain tu, kita tengok op-amp kan. Kalau misal kata macam you belajar dalam elektronik, kalau you punya open loop gain tu 100,000, so your error will be 100,000. Your error will be 1/100,000. Kalau your open loop gain tu ada setengah op-amp, open loop gain dia 800,000. Your error will be 1/800,000. So you will have a very small error. Maksudnya maksudnya dia punya output punya error will be very small. So that's the aim lah kalau you buat amplifier. You want to have the error as small as possible. Okay. Alright, so that is a tracking error. So you want to have the tracking error as small as possible. So kalau dalam sini ni tracking error dia kata kosong, which is almost impossible. So the error, tracking error ET is RT, which is your input minus your output. So if the system is dynamic, slow and stable, slow and unstable, or disturbance is affecting the process, ataupun when you buat model, your model tu bukanlah sebenarnya model yang betul, approximated model, so there must be some model error. Dia panggil model uncertainty. And then you have your measurement noise, ataupun kadang-kadang dipanggil process noise. You ada process noise, you ada measurement noise. So bila you measure, there will be some disturbance dekat dalam your measurement. So this is your model uncertainty, apa benda semua ni kita assume as a process noise. When you measure, macam radar kan, dia baca, dia track kapal terbang. So it cannot locate exact position. Beza antara exact position dengan apa yang dia measure electronically, that will be the error. So we want to make the tracking error to be zero, despite of the system is slow, unstable, ataupun there's a disturbance, uncertainty, and measurement noise. So to achieve the objective, so kita nak design satu feedback control yang satisfying the number of requirement. the stability in the nominal condition, kita nak ada stability in perturb condition, kita nak ada static performance, and then kita nak ada performance transience dengan frequency response yang can reject noise, adapt to the noise, and then will attenuate so that it will be insensitive to the noise punya measurement. And then kita nak controller tu to be feasible. Okay, nanti bila you belajar, nanti Prof Aini akan ajar, dia panggil apa nama benda ni, pole placement methods. Some of this pole placement is impossible to build. Sebab kita theoretically kita boleh bagi macam tu, macam ni, boleh macam tu, macam ini. And then kita tak boleh nak access the state itself. So kita estimate the state. So when you cannot access the state, you just estimate the state. Sometimes the state is not observable. So this controller is not feasible. So how can we do this? Okay. So the closed loop transfer function from the ratio, kita ada this ratio lah. You can ratio, and then we want to have a loop function which is just the controller dengan your system. So this is actually the loop function. So kalau magnitude of this loop function is 1, and then we will get the closed loop function to be 1, and the phase of the closed loop to be 0. So for every bounded loop function, we will get the magnitude to be 0. For this, if we have a system G of S, then we will choose the controller or the compensator to shape the loop function so that this will give us the bounded criteria that we set. And that's why this is called loop shaping. Kalau kita tengok yang sebelum ni, PID, kita tengok apa? Kita tengok dia punya poles dengan zero. Sama juga macam dalam your lead lag compensator. Kita tengok dia punya lead, kita tengok dia punya poles, kita tengok dia punya zero. So sekarang ni apa kita nak buat? Kita tukar semua dalam frequency domain. Kita tengok what is the closed loop frequency response, open loop frequency response, and then kita tengok error punya frequency response. Kita nak shape the error so that when the error comes into the controller will shape the error signals so that bila dia masuk dekat kita punya system transfer function, it will give us the output that we want. So kalau dalam frequency domain, kita banyak cerita pasal energy. When we bound the energy, the system will be stable. That's why kalau you still remember dalam your circuit theory 2, signal and system, Parseval theory, semua kalau system tu stable, bounded input, bounded output. We are talking about the energy. Bounded input energy, we will have a bounded output energy. So if you have bounded input, bounded output, the system is stable. And that is what we want. And that's what we are doing. So, apa yang kita tengok kat sini ni is the sensitivity function, which is 1/1 plus the loop forward loop punya function. So the sensitivity function is a complete, kita ambil apa the complementary to the sensitivity function. So this is actually the closed loop punya transfer function. So this is the complementary to the sensitivity function. So sensitivity function kita akan tengok kalau kita plot dari frequency response, kita akan tengok at what frequency dia akan be, it will be more sensitive. Kalau kita bagi apa anything at that frequency range, sama ada input ke, feedback ke, at that frequency range, the system will react instantaneously. So selalu kita fikir input cuma step, but sometimes the input is not step. If the input is not step, input can be sine wave, input can be triangular, input can be some other things. So if there is some change in the input and it's bounded, maksudnya dia ada limit lah, tak pergi infinite. Daripada 1 pergi 2, pergi 1 balik, pergi 2 balik, lepas tu pergi 0, pergi 2. So the input is bounded, the energy is bounded. Dia tak ada exponential pergi ke infinita. So kita nak the output also to be bounded. So kalau kita tengok sini, kita nak sensitivity to very small, so that we want to be immune. Kalau kita nak immune, the system must be insensitive. Kalau kita tak nak dia system sensitive, the error must be the tracking error must be small. Kalau tracking error small, so apa benda kita buat pun tak ada masalah. Sebab the tracking error is small. Kalau misalnya kita macam tracking error kita ada, say macam contoh op amp tu, let's say my tracking error is 1 over 10 million, my gain is 300,000, my output will be very small. So kalau saya ada apa nama ni transfer function and then complementary to the transfer function, if I add this thing up, how can we make this thing small? So the solution is to keep the sensitivity function to be small and low frequency. Then we have the open loop punya apa nama ni open loop punya system magnitude to be 1. So this thing will be very good for tracking. To keep the tracking error to be small at high frequency, then this thing will have a good noise rejection. Sebab dia macam ni lah. Saya bagi contoh lah, contoh. Sebab contoh dalam buku selalu tengok, contoh dalam buku nice ke, dalam buku apa nice, dalam buku apa yang pakai, Ogata. Contoh yang dia bagi tu terlampau ideal. Dia pun bagilah ada radar, ada kapal terbang, dia track. Bila you track kapal terbang, say this is kapal terbang. Say this is an aeroplane. This is the radar track. Bila you baca dia punya kapal terbang yang you track, you will get the range. Macam ni dia nak kira range. Dalam your EM class dia bagi pulse, tung tang, dia mantul balik daripada Doppler shift itu dengan apa dia punya time reflection, then you can calculate the range. Lepas tu dia tengok sini elevation banyak mana, azimuth banyak mana. Then you get your range, azimuth and elevation. So biasa benda ni dia scan. And then bila dia benda tu kan macam dish macam tu, bila dia pusing dia akan scan atas bawah. So this thing will give you the elevation. So apa yang dia kira bukan dapat secara terus is range dengan elevation. Range will be very difficult to find sebab dia akan bagi satu radar punya pulse, mantul, lepas tu dia tengok dia Doppler shift. So daripada Doppler shift range, you can estimate kapal terbang tu punya speed. So banyak benda yang dia sebenarnya dia tak dapat exact, dia cuma estimate aja. So kalau dia nak cari range, the pulse must be very small and very high frequency. So the error of finding the distance will be based on the pulse punya frequency, dengan dia punya chip. So there will be some limit. Mungkin dia punya accuracy tu lagi dekat, lagi bagus. Kalau jauh-jauh tu dia track. Kalau distance dia 10 km, mungkin error about 100 meter. Kalau dia dah dekat, error dia tu 1 or 2 meter. So this is the accuracy. Lepas pada tu, kapal terbang tu punya speed based on Doppler. So Doppler ni kadang-kadang chart dekat kapal terbang tu will also change dia punya Doppler punya reflection. So this thing will give you the measurement noise. So you cannot get the measurement as what you wish sebab there will be some noise associated to it. So this is bila dia punya chip frequency tu dia bagi kita nak dia accurate, so the frequency must be very high. So the higher the frequency yang kita bagi pulse pada kapal terbang, bila dia reflected, it will be high frequency also. So kalau kita feed everything up, we are feeding the high frequency to the system. So the performance specification in frequency domain, we usually refer to the regular closed loop system, to the similar second order under them. So we have this 1 plus 2 zeta over omega ns plus 1 over omega n square. So this is sama dengan s square plus 2 zeta omega n plus omega n square. Same thing, kita ambil omega n bawa ke bawah semua. Okay. We have the resonant peak, and then this is the maximum value. So this is the maximum value of the closed loop punya transfer function. And then the bandwidth of the closed loop system is the range of frequency at which the phase of the closed loop system is apa dia panggil 20 log, is about the amplitude in the log. So this is within the minus 3 dB. So this is the bandwidth. Kalau kita tengok bandwidth dia, daripada sini ke situ, macam dalam your electronic class lah. Daripada first knee to the second knee. So that will be your bandwidth. Daripada dia naik, lepas tu dia turun. That will be your bandwidth. So we are looking at the tracking of the constant set point. So let's say we have a RAM 1 over SK. So kita write the loop function in the body form, and then kita compute the limit t approaching infinity of the error using the final value theorem, and then kita will get this thing to be either 0, 1 over 1 plus k, or 1 over k. So this is depends on the value of h of k. H is the number of poles and zeros. So the constraint of the body gain of the forward loop will need some gain sufficiently large enough to bound the steady state tracking error man apa nama ni, poles to just 1 degree higher than your zeros. Contoh dia s square plus something something over s cube over something something. Okay. So when we look at the shape of the transient closed loop response due to unit step, we'll get the rise time, we get the settling time, and then we get the peak overshoot. So this is will corresponds to the 1 and then 2 zeta over omega n square, and then 1 over omega n square. So this is what it will correspond to. So the peak overshoot is the maximum relative derivation from the steady state. So this is the peak overshoot. And we have the settling time. This is about 2% or 5% daripada steady state error. Macam mana kita define? Kalau kita nak very strict, then will be 2%. Kalau tak, it's about 5%. So the rise time is the time taken for the steady state to go from 10% to 90%. So this is the rise time. Okay. So the relationship between the frequency and time response in the second order closed loop as a function of damping factor. So boleh tengok sini. So this is zeta dengan omega n. So the controller synthesis through loop shaping. So apa yang kita nak? Kita ada typical loop function as specified by H, and then kita ada tracking error in the steady state. And then apa yang kita nak? Kita nak some dynamic to the system. Kalau still remember black box punya eksperimen exam, macam mana kita nak dapatkan dia punya apa benda tu? Dia ada static, dia ada dynamic measurement. Static ni DC, dynamic AC. Same thing in this. Kita ada DC which is step, and then kita ada some AC function which is ramp, sine wave, and so on. So kita nak design a controller that meets all the specification in one shot. That can be hard sometimes, but in loop shapings, apa kita nak? Kita nak synthesize the controller that is designed in series of step, where C1 will satisfy the static specification, and C2 will satisfy the dynamic criteria. So kita kan ada buat dua. Macam dalam apa nama ni, your lead lag controller lah. You buat lead dulu ke, you buat lag dulu ke. Lag will do certain things, lead will do certain things. Sama juga dalam sini ni. Basically nanti bila you tengok lead lag controller ni is actually a loop shaping. Baik tak payah belajar benda ni kan. Sebab you tengok, oh, lead lag Sama je dengan loop shaping. Tapi awak belajar lead lag sebelum ni, you buat lead dengan lag controller, semua dalam S domain. You buatlah dalam S domain. Lepas tu pun tak tahu apa nak set. Nak letak pulse kat mana, zeros kat mana. Kita letak pulse kat sini, zeros must be 10 times. Letak sini, zeros must be 10 times smaller, 10 times bigger. Tapi kat mana nak letak pole? You don't know. So kita nak letak poles ataupun zeros first yang kita pilih tu depends on the bandwidth of the system. And this is what we are trying to do. And this is what we are trying to establish in this loop shaping. Okay, any questions so far? Saya dah cerita jauh ke depan dah ni. Benda dekat belakang lagi. Oh, semua pasang terus tidur. So in general form, tengok chat. Oh, tak ada. Okay. So in general form, kita punya C1, which is the static punya controller, kita nak the gain of our static controller and H to be the type of controller. So kita nak this, the G of S of this controller, then the gain is chosen by imposing the desired steady state tracking. So kita buat satu controller, dia akan settlekan masalah tracking error, steady state tracking error. So kita adjust dia tracking error, steady state tracking error. So if you still remember before this, steady state apa you nak buat? So you nak implement KP ke, PD KP ke, PI ke PD. So you buat this thing dulu. Once you have the steady state, once we settle with the steady state tracking error, then baru kita concentrate on the dynamic. So macam mana kita nak buat closed loop tracking error? Kita translate closed loop specification should be translated into a desired phase margin and the desired crossover frequency of the closed loop system. So we have kita kena approximate, kita carikan dia punya peak dia, magnitude of the peak, and then when the and then when we have this, we will get the frequency that produce the peak. So the next step is to synthesize the dynamic part of the controller. So the dynamic part is designed to guarantee the closed loop asymptotic punya transfunction is stable, and then C2 must be designed to satisfy the dynamic specification. So we focus on the controller that containing only real poles and zeros, no imaginary. Okay. So kalau kita tengok lead network, will provide the phase lead in the frequency range, certain frequency range. So the frequency range of the cut-off sampai dia habis cut-off. Sebab dia phase dia berubah kat situ. So it will be 2 decade. Kalau 1 sampai 100. Say cut-off dia kat 10, dia akan start daripada 1 sampai ke 100. So the maximum phase lead will be at midpoint. So this is the phase yang you bagi. The phase gain that you will give to the system. So this is the midpoint between the 1 decade earlier to 1 decade upper. So this is actually the peak of the frequency is at the cut-off frequency. So kalau kita ada sistem, kita implement the lead network, then this thing will be extended slightly to the frequency of interest. Okay. So the lag network will reduce the frequency gain. Kalau kita ada tu, it will tarik sikit ke bawah dia punya frequency response. Meaning that kalau kita punya sistem tu, ada certain tempat kita nak bring down so that we can get the phase margin. Ada certain part kita nak increase so that we get the gain margin. So we are playing around with the gain dengan phase margin. That's basically what we are trying to do. Okay. So, so saya cut short sebab masa dah nak habis. Ada seminit lagi. So this is the lead lag network. Now we are talking. So this form of a lead lag network, macam mana kita nak implement lead lag network dalam PID controller. Sebab PID controller ni dalam industri dia dah ada PID block. So how can we implement this thing? So we will implement the loop shaping dalam PID so that we can establish the PID using a loop shaping. So saya akan sambung sikit esok dengan minggu depan. So minggu depan ada sikit loop shaping dengan loop shaping plus introduction to digital control. So esok you hantar assignment, hantar dekat iFolio. Esok kita akan review the assignment yang saya bagi, which is a transfer function. You implement Ziegler-Nichols dengan Cohen-Kuhn. Lepas tu, macam mana based on these two and based on your observation of implementing PI dengan D and open loop, you buat visual tuning. So bila visual tuning, tak akan ada benda yang sama. Tak macam Cohen-Kuhn dengan Ziegler-Nichols. Kalau pandang gunung tu cantik, tak semua orang cakap gunung tu cantik. Kalau tengok kereta Proton X70 tu cantik, tak semua orang cakap X70 tu cantik. Macam tu lah. Dia tak akan, kalau what is your favorite car? So it's very difficult to have, you know, satu whole class. Ada 4 kereta je dia suka. Impossible. Sebab the way you tune, how much gain yang you kena bagi must differ from person to person. Tak akan ada satu orang yang dia masuk gain macam ni tak akan ada yang sama. Sebab pertimbangan untuk visual tuning tak akan sama. You just have a basic guideline what you should do first, and you look at it, you implement gain, you tengok what happen. So gain yang you pilih, let's say you pilih gain 3, your KI dengan KD will be different than orang yang gain 4. Apa yang you nak buat, so you tune must have steps saya dah bagi, tapi this will require multiple iteration. So esok bila you bagi, you kena bagi reason kenapa you pilih gain yang you ambil, and kenapa you pilih KD banyak tu, kenapa you pilih KI banyak tu. Okay, so that will be tomorrow. So esok mungkin kelas kita slightly more than 1 hour. So as I told you in the WhatsApp, you can go to the CTMS punya website, practice macam mana nak implement PID. Daripada situ esok you boleh implement esok kita punya kelas is basically pure MATLAB. So question and answer, show me what you have done. Saya akan pick at random untuk orang present, then submit. So mungkin lepas sejam submit, lepas pada tu mungkin lepas setengah jam you submit, lepas pada tu I'll choose at random to give to get your your opinion on the P that you pilih, I yang you pilih. So nanti kejap lagi I will do short write up what is the things that I'm looking for untuk your assignment esok. So saya dah bagi the transfer function. Esok saya nak tahu kenapa pilih gain banyak tu, kenapa pilih gain KI banyak ni, kenapa you pilih gain KD banyak tu. So tak akan ada orang yang sama. It is not a good idea to start dengan Ziegler-Nichols ataupun Cohen-Kuhn, sebab untuk motor dia tak sesuai. So kalau you pilih KP, KD, KI tu pakai Ziegler-Nichols, then you can see lah macam mana the system will suffer. So esok dalam assignment saya akan minta tu lah. So you will have about 15 minutes to do short write up on your opinion of the effect KP, KI dengan KD yang you pilih based on visual tuning. Alright? So I'll see you tomorrow at 2 o'clock. Mungkin kita habis lewat sikit daripada pukul 3. Any question? Let me look at chat. Kalau tak ada, so good luck for your assignment tomorrow. Tak payah, kan saya dah cakap dah, awak ni tak baca betul lah. I told you dalam saya punya write up description tu, you buat Ziegler-Nichols, sebab dia buat Ziegler-Nichols kan. Ziegler-Nichols dengan Cohen-Kuhn. Tak payah yang itu dia punya paper, dia buat CHR tu, saya suruh you redo Ziegler-Nichols dengan Cohen-Kuhn. And then you boleh compare result lah. Anything? Kalau tak ada house, boleh. Visual tuning can use PID tuner in MATLAB. Boleh, lagi cepat you buat. Kalau nak menipu pakai PID tuner pun boleh. Lagi cepat. Tak ada masalah. Tapi you nak pilih, you tak boleh nak pakai auto tune dia lah. Sebab bila you pilih auto tune dia, you don't know apa dia punya pertimbangan untuk dia ambil KP, KI dengan KD. You have the value, but you don't know kenapa dia pilih gain banyak tu. MATLAB will not tell you why KP banyak ni, why KI banyak ni, why KD banyak tu. Because yang saya nak, bila you pakai visual tuning, kenapa you ambil KP banyak ni, kenapa you ambil KI banyak ni, kenapa you ambil KD banyak ni. It is not this. It's not the answer that I'm looking for. I'm looking for the reason why you choose certain things. Alright, Aileen. Anything? So if you have anything, saya bagi masa dalam setengah jam to for you to ask me pakai WhatsApp. Lepas pada tu dah habis kelas baru nak masuk. Lepas pada tu I will not entertain until tomorrow. Nanti kan ada yang hantar mesej pukul 1 pagi. Sabar-sabarlah, tunggulah pagi. Alright. So kalau tak ada apa-apa, I'll see you tomorrow. Stop share. Okay. Recording. Stop recording.